Okay, so let us consider this first example here. We have a 3-hinge arc here. We have the bars that is carrying this horizontal member here, and along that horizontal member there is a 500 pounds per foot loading. So as we can see here, we need to determine the loading at point D, so that we are going to show that the arc is subjected only to axial compression at any intermediate point like point D. So basically we are going to have the idealized structure for this first, and we note that in every length here, since this is a spandrel, we can use the equation of the parabola. We can also use this spandrel as a basis, or this largest spandrel here, and just proportion it to the smaller one, and that is the smaller one. That is why this equation was derived here. So how was that? We'll just have to ratio the y is to the y of the smaller spandrel, and the x is to x of the larger to the smaller spandrel. So we used y first, that is 25. Okay, and then proportion it to the square of the x, which is 50. And y is 50 because x here is bending, and it is actually bending downwards. That is why it is indicated. We have indicated negative here. So we have to indicate it by a negative sign. And then this will be further equated to the smaller spandrel. So if this small dimension here is y, and this is x, we can say that y is to x squared. So by cross multiplication, solving for y, we have this equation. Actually, this is the equation here. So moving on, we are going to have the idealized structure here, naming our A, B, and C points. So first, we are going to consider the whole structure in order to come up with AY and CY. And it is just sharing the symmetrical load here. And this 500 pound per feet can be resolved into its resultant here, that is 500 times 100, and that is actually 50,000 or 50k or 50 kips, because 1,000 kips or 1,000 pounds is 1 kip. So this is 50,000 pounds actually. So by that we can employ summation moments at both supports in order to determine AY and CY. However, AY and CY will just have the shared. We'll just have to share 50,000 here. So therefore, both will have a 25,000 pounds reaction. So AX and CX will be determined by separation. So if this is the separation considering the right portion, there will be BX and BY here, and CY and CX. We just write CY here, 25, and of course, this was already bisected the distributed load. So if this is 50 pounds per feet, just multiply that by the distance 50. So 25 times 50, or sorry, 500 times 50 is actually 25k. So in order to determine CX here, we now take moments at B. So we have first 25k times 25. Then the CY, negative rotation, 25k times 50. And then plus CX, a clockwise moment, times 25 is equal to 0. So we can now solve CX to be also equal to 25k. Okay, by summation forces horizontal, we can just say that BX is also CX, and that is actually 25 kips or 25,000 pounds. So knowing all of the reaction, so let us have to consider here point D. Okay, so this is point D. Okay, and then we need to illustrate a section at D. And at that section, we can obtain this. Okay, so we have a section here or a cut section from this D. And if this is the cut section AA here on the left portion, we need to indicate a force horizontal here. Say this member here, but this member shall carry no loading because this horizontal pin here is carried by your arc here. So we indicate a zero force member on that horizontal member here. So if we are going to determine all of the force transmitted on the bended member here, we need to indicate the shear that is perpendicular to the member, this one, and the normal force that is parallel to the member at point D. Say that is the parallel member. And of course, there will be a bending moment at point D. And so the bending moment could be derived by the three equilibrium equations as well as the VD and the normal at D. So VD is the shear at D and D is the normal at D at this particular point here. So at that particular point, we need to know the slope so that we can work on the components. Okay, so in this figure, it was already indicated, or the angle was already indicated, and where this angle came from. So this angle actually came from your slope D. And recall that our equation is this one. Y is equal to negative 25x squared all over 50 squared. I'll just bring it in here. So why do we need to have the y equation? Because y equation could be derived so that we can have the slope. Because remember that the differential of y with respect to x is actually the slope or the tangent theta. That is why this is rise all over run, or vertical all over horizontal, or the difference is actually the slope, which is equal to tangent theta. So we derived y with respect to x, and that becomes dy over dx. We copy the constant and then derive x squared, and the derivation of x squared is actually 2x. And further, if we are going to have to simplify this, 25 times 2 is negative 50 all over 50 squared, is we have a result of this one. Okay, so one of which will cancel, so that your dy over dx becomes 1 over 50x. So where is d located from your x? Okay, so d is located from your x actually 25 feet from C. Okay, so actually that is your reference. Okay, we just say here that when x is 25, we have 25 over 50, which is equal to negative 0.5. So we retain the negative there. Anyway, negative just simply indicates that your slope is decreasing. Okay, so with that, remember that dy over dx is actually tangent theta. And your tangent theta will be equated to negative 0.5, so we can get the angle. So that angle will be equal to 26.57 degrees. That is why this indicated here the angle, 26.6 degrees. And it is actually referred to the horizontal line. So we can see that your normal is inclined at the horizontal line. Okay, remember this. that if you have an angle here and then draw a perpendicular to this angle, okay, so this is perpendicular combined with the vertical, then this will be also the angle. So same true with this. So your normal at D is 26.6 degrees, and then remember that VD, or the shear at D, is actually perpendicular to your point D here, so that combining with the vertical line, this is also 26.6 degrees. So angle is very important to determine the component here, so that we can actually work with the unknowns. So working with the unknowns, we'll just have to apply the three equilibrium equation and the moment for the moment at D. However, where 6.25 came from here, we'll just have to go back to the y equation. So this is the y equation, okay? And then what is your x, where your height is unknown. So say this is y, our y, or let us label this as our y, okay? So label that as our y, and then this is our y, being proportion to the larger spandrel a while ago, and your x is 25, okay? So we'll just gonna use this equation. So when x is this one, that is 25, we'll just try to substitute it in this function. So therefore, calculating that one, we will have actually 6.25. So why do we need to have 6.25? So that if we're going to take moments at D, then we can compute for the value of the moment at D. So let me just highlight that one. So first, we are going to summation forces along X is equal to 0. So first we have rightwards 25, and then normal at D is actually leftwards, and it is adjacent to your reference angle 26.6 degrees. So we're going to use cosine function. So I'll just move it a little left here, and then your shear at D would be towards leftwards also, but your component, horizontal component, is opposite your reference angle. So that is using sine function is equal to 26.6 degrees. So we have ND, VD towards left, and 25K towards right. So we can equate it to 0. So we also simplify this. Let us transfer your constant on the right side, or just these two on the right side. We have this equation. So I'll just delete this and then say this is equation 1, to be supplemented by another equation formed by this vertical summation. So on the vertical summation, starting with the normal at D. So where's the normal at D? So here it is. Normal at D on the vertical will be towards upwards, and the component is opposite the angle 26.6 degrees. And then for VD here is going downwards with the component adjacent to the reference angle. So we're going to use cosine 26.6 degrees here as a multiplier, and then this distributed load here, okay? So the distributed load is 500 times 50. Okay, so this is actually 500 times 50, or we should say 25. So this is 25, okay? 500 times 25 is 12,500 pounds or 12.5 kips. Okay, so this is the result, 12.5 kips, and that is towards down. Okay, so equate this to 0. So we again simplify, bring your constant to the right side, then we'll have this second equation. So we have two equations with two unknowns, the same arrangement, where constant at the right side, we'll just have to calculate the value of ND and VD, or the normal at D and the shear at D. And we will be having this result. So actually, if we are going to stick with the angle a while ago, that is 26.57, ND will be rounded to 28 and VD will be almost equal to 0. So as we have the result, we have just proven that we have an almost equal to 0 shear here. So actually this could be rounded to 0 because this cosine 26.6 here was just rounded to this number, and actually the original value is 26.57. So anyway, these are the results, and then now we are going to take moments at D in order to solve the couple at D. So doing that, we have summation moments at D is equal to 0. So at this point, we consider here 12.5 times 12.5 feet, and that is actually a negative rotation plus this one, 25 kips times 6.25. So this will be equal, we deduct MD or the couple at D and equate it to 0. And actually we will end up with a value equal to 0. So that is why you have just proven that your shear here is negligible, as well as the moment will be equal to 0. So in most cases, your bended member here will be tend to have a normal force, or that is an actual force actually. So ND is the normal force at the slope D. So that is for this problem. Let us try another one. So in here we have another 3-hinge arc tied is subjected to the loading as shown in figure. So we have this again, the idealized structure. We are bound to determine the force CH and CB. So remember that horizontal HGF has no loading. That is why it is very clear in the problem. The dash member of GF of the truss is intended to carry no force because there will be no lateral force present on the arc. And actually it is just supporting vertical loadings, namely 15, 20, and 15 here. So as we can see, there will be a horizontal connection between A and E. So if we're going to have our free body diagram, remember that E here is supposedly roller, no? Supposedly roller, in order to attain the determinacy of this structure. That is why we have two reactions at the pin at A and the single reaction at the roller at E. So you can see here. So therefore, we are going to have the free body diagram of the entire arc, considering all of the whole structure here. And then we are going to take moments at E. And upon E, you can see that AX has no moment arm. Will just be eliminated on the equation. So EY Where's EY? Or we are taking moments at A. Okay. We have first EY, that is having a counterclockwise moment. So this time, a counterclockwise moment is assumed to be positive, and a clockwise is assumed to be negative. So anyway, it is the sign convention on this book. We'll just yield to the same result if we stick to a sign convention that we usually do. Okay, so EY 12 and then 15 here times 3. So this 15 here times 3, and then 20 times 6, another 15 that is multiplied by 9, and that will be equal to 0. So solving for EY, we have this one, this result, 25 kilo Newton. And then AX here is obviously would have no value because there is no horizontal force. Okay, so AX has no value. By summation forces, X is equal to 0. So we do the third equation, and as we can see, it will just yield to 25. And obviously we do not need to do moments here because it is just symmetrically loaded. Okay, and if it is symmetrically loaded, we'll just have to add these forces, and 15 plus 15 is 30 plus 20, that is 50. Just be shared by these two vertical reactions, AY and EY. So each of them will have 25 kilonewton vertically upwards. And then we are going to cut the section on the mid, of course, that is a treatment in the 3-hinge arc. So we cut that on the mid. Okay, so at the midsection we have this. So this is being cut, and it was already stated in the problem that this member will carry no horizontal loading, and usually this top member here has no horizontal since, well, there is no lateral force applied here. So that is the treatment, and usually most of the loading will be carried by the arc here. Okay, so by that we are actually getting here the first at AE, or this is a bar actually connecting A and E. So we take moments at A to solve that. Okay, or sorry, moment at C, sorry, it is. So we just take moment at C here. We have summation moment at C, so this is C. So 20 has no moment arm. So the force, this force FAE times 5 minus this reaction, 25 times 6, and then plus 15 times 3. Okay, so this will all be equal to 0, and that will be equal to 21 kilonewton. So 21 kilonewton is our horizontal force member AE. Okay, and then we are going to perform here summation forces X and Y. So we go back to this summation forces X and summation forces Y. So we have this, we have rightwards FAE. By the way, FAE is obtained to be 21. So that is a rightwards. We have 21 minus CX is equal to 0. So basically this is 0, so we do not need to include that. Therefore, Cx will just be equal to 21, same as FAE. Then we proceed to summation forces Y. So we have summation forces Y. What are the Y values? We have negative 20 going downwards minus going downwards 15 plus going upwards this one CY. What else? We have plus 25. So we have to equate it to 0. So therefore, our CY is equal to 10. Okay? So Cx is 21, Cy is equal to 10. So we can see here, Cx is 21 and Cy is 10. So with that, we can isolate actually this, okay, or the joint at joint G. Okay, so where's that joint G? So here's the joint G. So we isolate joint G. So at joint G, these values are 0, of course. 0, and then this is 20. And you remember GC should be equal to 20 also. And that will eventually transfer to your joint C. Okay? So at joint C, we'll have this X and Y axis here. Say this is the GC equivalent to 20. Then we have these two members here. Say this is BC and what's that? CB and CH. Say this is CB and CH. Now we need to know the angle here. So obviously if we use this triangle here, okay, so if we're gonna use the triangle, you have here a bottom dimension of 3 and this is 1. So obviously we can get the angle here, say theta. Okay, and tangent theta is just equal to 1/3, so that we come up with an angle of 18.43 degrees. So if we're going to use this one, okay, just indicate the angle here, 18.43. So this is the illustration here. Okay, Yes. Summation forces vertical and horizontal. Okay. So we have summation forces along x is equal to 0. We have this one, negative ch times cosine 18.43, and then another minus cb cosine of 18.43, that is leftwards, and then minus 21 is equal to 0. So we can rearrange terms here. Negative ch cosine 18.43 minus cb cosine 18.43. So this now becomes 21 to the other side. Say this is equation 1. And then summation forces y is equal to 0. We have an upward ch times sine 18.43 minus cb times sine 18.43. Okay, so that is downwards, and then another downwards 20 and an upwards 10. So we can actually continue. Say simplifying this one and then transposing to the other side of the equation. You just have to copy that one, ch sine 18.43 minus cb sine 18.43. So this is positive 10. Say this is equation 2. Then we will be having two equations with two unknowns here. So we obtained a CH of 4.75 kilonewton positive. So meaning we have assumed it correctly. So if this is assumed correctly, this is tension. Okay. And for the other one, we have CB equal to negative 26.88 kilonewton. So negative means it is assumed on a wrong direction. So CB is otherwise positive 26.88 kilonewton. So it was assumed initially to be tension. Therefore, this should be in compression. So this will be the solution for the second problem. Okay, so thank you for listening and have more practice.